Okay, welcome to 5.4 homework. I've taken the liberty of doing some pre-work on a diagram. I'm going to just discuss problems 2 and 4 in this short video. And let's get started here. Problem number 2 says, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and what are its dimensions? This is a heck of a little problem as far as calculus is concerned. My assumption might be, I realize as A gets longer, if 5 is fixed, B is getting shorter and shorter until A becomes close to 5, B becomes close to 0. We get 5 times close to 0, 0. Same argument as A gets really smaller and close to 0. I believe that probably calculus is going to support that our largest area would be when A and B are equal. But let's get started with this. I can say that the area is a function of A and B. It is 1/2 times the base, which I'm calling A, times the height due to the right triangle, B. I also know that A squared plus B squared has to equal 25. I don't want the area as a function of 2 variables. I want the area as the function of a variable. So I'm going to solve for either A or B. Doesn't matter. In this case, I always choose the easier one to solve for, but it's the same. 25, we would subtract B squared. We would normally take the plus or minus square root, but A is not going to be a negative number, so it's positive. Therefore, A up here can be replaced with B. And I'm going to write that rather than square root as to the 1/2 power in preparation for taking the derivative. So I get 25 minus B squared to the 1/2 times B. So this is area as a function of just strictly B. And likewise, we could have very, very similar equations with area as a function of A. All right, here we go. A prime B. We want to know when the slope is 0. So, product rule, this times this. The derivative of the first is 1/4 times 25 minus B squared to the negative 1/2 times the inside derivative, negative 2B, times the plain old second function B, wow, plus the plain old first function, 1/2 times 25 minus B squared to the 1/2 times derivative of the second function, which is 1. All right, let's do some simplifying here. Here I'm going to get a negative 2B squared on 4. So that is negative B squared on 2, but this can go to the denominator as 25 minus B squared to the 1/2. Plus 25 minus B squared to the 1/2 on 2. And as often is the case on these ugly looking things, factoring or getting things simplified isn't quite as bad as we might think. Our least common denominator includes a factor of 2, a factor of 25 minus B squared to the 1/2, a factor of 2, but I've already got it. Good news, this negative B squared was already over all of that. More good news, this term, this numerator was already over 2, and I just need to multiply it by 25 minus B squared to the 1/2, but that's perfect when I do that, because that and this just cancels the square root. So this becomes plus 25 minus B squared. So A prime B equals negative 2B squared plus 25 on 2 times 25 minus B squared to the 1/2. Now, if we realize that A has to be, or B has to be less than 5, that keeps the denominator from ever having a 0 or a square root of a negative. So this is differentiable everywhere. We're only interested in when the numerator is equal to 0. If we set this equal to 0, that's when the numerator is equal to 0. That happens when, flow charting here, when B squared equals 25, negative 25 on negative 2 or 25 on 2, or when B equals square root, that would be 5 on root 2, so 5 root 2 on 2, which is what we suspected. If this is 5 root 2 on 2, A is as well. You can go through that work as well. So A is 5 root 2 on 2. So that would produce the largest area. When we multiply those guys together, we get volume is 1/2 A times B. I get, running out of room here, 1/2 times 5 root 2 on, actually I'm going to do it this way. Now I'm really running out of room. 1/2 times square root of this would be 5 on root 2. 5 on root 2 times 5 on root 2 is 25 on 4, and that would be, what was our unit here? We were in centimeters, centimeters squared. Sorry about that. Should have started a little bit smaller. I think I'm not going to re-record another video though, so we're going to move on to number 4. Number 4 says, show that among all rectangles with an 8-meter perimeter, the one with the largest area is a square. Now, I would not expect that to be unique to 8-meter perimeter, but that's what we have to work with. So, we are interested in area. Area as a function of A and B is A times B. And we also know that our perimeter would be 2A plus 2B. I don't want two variables, I want one. I'm going to solve this for A, and I get A equals 8 minus 2B divided by 2, or A equals 4 minus B. And if A is 4 minus B, then we can replace A with 4 minus B, and I get area based just on B is 4 minus B times B, or area based on B is negative B squared plus 4. First derivative is negative, plus 4B, excuse me, is negative 2B plus 4. When I set that equal to 0, I get B equals 2. And if B is equal to 2, then A is equal to 2. Therefore, the rectangle with perimeter 8 and largest area is a 2 by 2 square. Okay, so that's just the first two problems. More to come.